So in number 29, we have a conducting rod of radius 1.3 millimeters and a length of 11 meters inside a thin-walled coaxial conducting cylindrical shell of radius 10 times that of the same length. A net charge of 3.4 times 10 to the minus 12 coulombs, that is and the shell has negative that magnitude. What are the magnitude E, and the direction, radial inward and outward, of the electric field at a radial distance of R equals 2R2? So this is outside of this whole thing. So first of all, imagining that, where R is that distance, using Gauss's law, we can plug in again, removing E outside of it. Integral of dA is just going to be 2 pi RL. And the charge inside of this is going to be both the charge on the rod and the coaxial conducting cylindrical shell. So I'm going to call it Q1 and Q2. Plugging it, or just solving it that way, rearranging things just a little bit, and then plugging in our numbers, remembering that the charge on the outside piece is going to be double and negative double the charge on the inside piece. Finally, down below here, this is a little confusing. You might remember that the outside piece, or this whole thing, is at a distance of 2R2. But again, remember, R2 is 10 times R1. So we've got 2 times the 10 times the radius of that inner piece, which is 1.3 millimeters. Solving that, again, the length is 11 meters, that's given. Solving this, we get the electric field is that. Now, because this piece here has twice the negative charge of the other piece, this is much more negative than the other one is positive. So what's the electric field going to be doing? It's going to be pointing inward at each and every point along here. So the correct answer on this one is that B, it's pointing inward. C is, all right, what's the electric field when you're at a distance that's 5 times this inner part? Well, on this inner piece here, and this is kind of hard to visualize on this one, we're asking for a point somewhere in between these two things. Well, the electric field inside of here is just going to be the charge to the inner conducting rod. And so when we do our Gaussian surface inside of that, we're only talking about the charge on this inner piece, which is just this number right here, Q1. Solving this, we can find the electric field is this. And which way is it pointing? Well, in this case, this is a positive charge. It's going to be pointing outward at each and every point. So the correct answer for D is outward. Finally, E and F ask what's the charge on the interior and exterior surface of the shell. Now this gets a little bit more interesting. We know the inside of this thing is charged to this value, and by the way, since it's conducting, that charge, all this positive charge repels each other and is going to be on the outside surface of this conducting rod. Forgive me as I draw these real quick. But now there's something interesting going on. We know that inside of any conductor, the electric field is always, always, always zero. And if you use Gauss's law, so we know inside of this, the electric field is zero. But how is that possible if we've got positive charge inside of this conducting shell? Well, what must be happening is this. There actually must be a charge or induced charge of exactly negative 3.4 times 10 to the minus 12 on the interior shell of this thing. That way, if you put a Gaussian surface inside of this light blue conducting shell I've drawn, the total charge inside would be zero. Why? Because we have exactly as much negative charge as we have positive charge on this rod here. But we also know, interestingly enough, that this shell has twice the charge, or twice the negative charge, as the positive charge inside. How's that possible? Right now it's an equal. Well, what must happen here is on the outside, there must be an additional negative 3.4 times 10 minus 12, so that the total charge on the shell adds up to twice the charge of the inner one, but negative. It's a little bit strange, but yeah, we've got also a negative charge here. What would the field lines look like around this whole thing? Well, it gets a little exciting. On the inside here, they're pointing outward. And then on the outside, they're pointing inward because of the net negative charge on this whole thing. And I guess I could probably draw a few more in here. It's kind of a fun electric field diagram, if that makes sense. But yeah, we end up with this very interesting field situation. Hopefully that helps. Again, there'll be a field line coming down here. There's more down here. I just can't draw them all. And there's some down below. But that's what this looks like. Good luck.